students, Professor Nugent here. In this video, we are going to discuss interactions between continuous and binary variables. Look at this regression. The regression, let's put a big, nice rainbow star. Rainbow star. This regression, yi equals beta naught plus beta 1 times di plus beta 2 times xi. D is a binary variable. X is continuous. So d is either 0 or 1. X is measured on a spectrum. As specified above, the effect on y of x holding constant d is equal to the OLS coefficient beta 2. Does not depend on d. We want to allow the effect of x on y to depend on d. So the effect of x on y will be different for different groups. So we want to include the interaction term di times xi as a regressor. So we're going to create a new variable that is di times xi. This is the new variable. And then we're going to have a new coefficient 2. And we're going to run this regression. Double star, rainbow stars. Perfect. This is the regression that we're going to run. Now let's talk about what these two regression lines look like for the different groups. So we have a d equals 0 group and a d equals 1 group for this regression. When d equals 0, that term drops out, that term drops out, and you have yi is equal to beta naught plus beta 2 times xi. That is the d equals 0 regression line. Now, for d equals 1, oh, we need to bring these ones back in. Now, this thing is equal to 1, and this thing is equal to 1. So the d equals 1 group is yi, that's equal to beta naught plus beta 1 plus beta 2 times xi plus beta 3 times xi, right? This beta 1 comes from the second term up here. The beta 3 times xi comes from the interaction term. Now the D1 regression line is summarized as follows. You have a different intercept from the d equals 0 regression line and a different slope from the d equals 0 regression line. The slope is beta 2 plus beta 3. The intercept is beta naught plus beta 1 for the d equals 1 group. Let's look at this on a plot. We can have, really there are just two different scenarios. On the left, we do not have the interaction, there's no interaction term. There's no interaction, so the difference between the two lines is just the shift in the slope, that is the beta 1. Okay, the slope is the same for both groups. But in beta 2, in plot chart B, you have the interaction term as we discussed in the last slide. So for line 1, that is the d equals 0 group, where the intercept is beta naught and the slope is beta 1. For line 2, that's the d equals 1 group, where the slope is beta naught plus beta 2, the slope is beta 1 plus beta 3. Now, this chart down here, this is kind of a weird chart that would occur if you didn't include the dummy variable as its own distinct individual term. And we just don't do that, so we're not going to pay this much attention, because if we don't include the dummy variable as a distinct term in the regression, then we have to be able to make some very specific and restrictive assumptions about the data that aren't usually plausible in practice. So we're just going to typically include any variables that are in an interaction we have to include them by themselves in the regression. Alright, so the general rule, as before, we want to compare the various cases, the d equals 0 versus the d equals 1 case. And here we're going to see that the effect of x on y will depend on d. So the change in y given a change in x, that's going to be beta 2 times the change in x plus beta 3 times d plus the change in x. So if d equals 1, then we get this whole term for the change in y given a change in x. If d equals 0, then we only get the first term. And what this means is that the change in y for a change in x is different for different groups. Alright, folks? So this is the what we see here. This is like the marginal effect, and it is different for different groups. For the d equals 0 group, you only have beta 2. For the d equals 1 group, you have beta 2 plus beta 3. So the effect of x on y depends on d, which is what we wanted, and beta 3 is the increment to the effect of x on y when d equals 1. Let's look at an example. We're going to look at test score, student to teacher ratio, and high EL, which is going to equal 1 if the percent of students learning English is greater than 10. We have this regression. Let's put a big old rainbow star. We're looking at this regression. The predicted value of test score is equal to 682.2 minus 0.97 times the student to teacher ratio plus 5.6 times high EL minus 1.28 times student to teacher ratio times high EL. When high EL is equal to 0, the third term drops out. We don't have the fourth term either because those things are equal to 0, so we only have 682 minus 0.97. When high EL is equal to 1, we have both of these things come into play. So we have 682 minus 0.97 times the student to teacher ratio plus 5.6. High EL is equal to 1, so we get 5.6 minus 1.8 times the student to teacher ratio. So observe that we get a different intercept, 687.8 versus 682.2, and a different slope, negative 2.25 times the student to teacher ratio versus negative 0.97. So we have two different regression lines with two different intercepts and two different slopes. The class size reduction is estimated to have a larger effect when the percent of English learners is large. So the effect of x on y is different for different groups, and using this interaction term allows us to demonstrate that. This is so cool! Taking this a little bit further, let's pay attention to the statistical significance of these things. The two regression lines, we can test the null hypothesis, H naught. The two regression lines have the same slope. This null hypothesis is testing the statistical significance of the coefficient on the student to teacher ratio times high EL interaction, that being equal to 0. The test statistic is negative 1.32, so we would fail to reject that null hypothesis. We could also test the null hypothesis that the two regression lines have the same intercepts, which is testing the null hypothesis that the coefficient on the dummy variable high EL is equal to 0. That test statistic is 0.29. Again, we would fail to reject that null hypothesis. However, it is important to do a comprehensive statistical inference evaluation, carry out a null hypothesis on this statement being the two regression lines are the same. Are the two regression lines the same? That is a joint test of statistical significance of the population coefficient on high EL equal to 0 and population coefficient on STR times high EL equal to 0. So we're testing the joint statistical significance of these two things. And the F statistic is 89.94. It's huge. The p-value is 0.001. So we would reject that null hypothesis that the two regression lines are the same. How could that be that individually these coefficients are insignificant, but jointly they are significant? Let's think about why that would be. Well, folks, what's going on here is that we're likely to have imperfect multicollinearity going on. Imperfect multicollinearity, which means that we're going to have large standard errors, right? This coefficient is the effect on test score for a change in high EL holding this thing constant. Oh, that's hard. Holding this thing constant when high EL is in here too. Folks, that's going to give us an imprecise estimate of this coefficient, of the 5.6 coefficient or the negative 1.28 coefficient. We're going to get imprecise estimates with large standard errors because of that imperfect multicollinearity. However, just because the coefficients are imprecisely estimated does not mean that their joint significance is also basically zero. All right. So we have shown using a joint null hypothesis that these two terms enter the equation and the two regression lines are different. All right, folks, that is it for interactions between a dummy variable and a continuous variable. In the next video, we will cover the last kind of interaction, which is interactions between continuous variables.